So hello everyone, can you hear me?
Yes.
Okay, that's good. Make sure you can see my screen. I will start very soon.
Is what we're doing today going to be on the test?
Yeah, so what we are going to do, so the topic we have today won't be included in the exam. Okay. Yeah, so this is some actual topic we can go through because we have more time left. But if you are a PhD student and you plan to do a qualified exam, so this content is useful. Okay.
Okay, thank you.
Yeah. And if okay, so let's start right now. This is the last lecture. So after today, so we won't have any more lectures. So we will have final exam on the May 18th, Monday. Okay. So starting from 5:30 p.m., 24 hours open book. And the final exam will be comprehensive, which means that it will cover all the contents of the class, even including the contents we already, including the contents before the midterm exam. Okay, but we will have more problems focusing on the new contents. It's like 60% of the exam problems will focusing on the contents after the midterm exam. So the other 40% will be the old one, which before the midterm. The next week I will still hold my office hour. So if you have any question, you can still ask me the question at that time. And if you need additional more times, you can write me an email so that we can schedule some time if you need more individual office hour time with me. Okay. Today's topic is we are going focusing on the two-phase flow. And because it's convection, so which is involving to the fluids, so we are more focusing on the two specific kinds of two-phase flow: boiling and condensation. Boiling is between they are all between the gas phase and the liquid phase, right? So both gas and liquid we consider they are fluids. So boiling is from the liquid to the gas, and condensation is from the gas to the liquid. So first, we will separate the topic, today's topic in two parts. The first part we will focusing on the boiling, and the second part we will focusing on the condensation. So let's start with some basic concepts for the two-phase problems. And the first thing we can, this will remind you some of your thermodynamics class contents actually. So the first thing is the phase diagram. Okay, so this is a typical TP diagram for the TP phase diagram, okay, temperature and pressure. We have two special points here. The T point is called the triple point, okay. At the triple point, you can see that, which is actually the solid and liquid and vapor. And these three phases is drawn as the triple point, which means that at this point, it's possible that, you have three phases, coexisted at the triple point. You can have the solid phase, liquid phase, and vapor phase coexisting, okay. This line here between the solid vapor, okay, this is the phase changes. You can, cross this line, you can have the phase changes between the solid and vapor, right? From solid to vapor, we can call it, they are called sublimation. And from the vapor to the solid, you can call the deposition, okay. And between the liquid and between the solid and liquid, this line here, if you cross the line, we will have like so phase changes, like from solid to liquid, we can see the melting, okay, or fusion. From the liquid to the solid, we can call it the solidification or crystallization, okay. But in this class, we are not focusing on these two lines, okay. We are more focusing from this line between the liquid and the vapor, okay. You can see that this line will ending at another point called C, right? This C point is called the critical point, okay. What the critical point means? It means that if you have a temperature or temperature larger than this critical point, or you have pressure larger than this critical point, actually you can not really can make a make the difference between the liquid and the gas, okay. Which means that the bond between the liquid and the gas is very, not even become not clear. Okay, you can see that this at this stage they are either it can be both liquid or they can also be called by gas. So in this stage we can call the supercritical condition. Okay. If you do research, okay, the most significant behavior of the supercritical conditions is that there are some physical properties like those mu, Cp, rho, actually K. Okay, they will change dramatically. Okay, with the temperature and pressure. Okay, so but we will not talking about that. Okay, at this point. So between this T point and C point, this line here, so we will have the phase changes between the liquid and vapor. From liquid to vapor is the boiling or evaporation, and from the vapor to liquid we call it condensation. Okay. The next concept is so-called two-phase equilibrium. Equilibrium basically means that at this equilibrium condition, the two phase, okay, either gas fluid, solid, or solid gas, they can coexisting. Okay, they can coexist at the steady state. Okay, so which basically, if you're looking at this diagram, which means that the point is basically is falling on this solid, on these three lines actually. So they are calling the equilibrium states actually, two-phase equilibrium. In the thermodynamic view, okay, that basically just means that on this PT diagram means that your P and T is fixed, okay. And in that case, that means that if you have the thermal equilibrium between the liquid and the vapor at this any point on this line here, it simply means that your Gibbs free energy, okay, this is small g means specific, okay, means that per kilogram, okay, which means that the Gibbs free energy of the liquid is just equal to the Gibbs free energy of the vapor. So that's why that there are no further phase changes. So that's why when they're falling on this point, so they can reach equilibrium. Okay. One thing you need to keep in mind is that there are when we do the engineering analysis, right? We have usually will have these two state need to consider. one is like a general thermodynamic state, okay, which means that any point on this 2D plane or any or maybe on P row plane, P row plot or T row plot, basically means that if you want to define a thermodynamic state, okay, you need at least 2 independent state variables. It can be either pressure, temperature, density, temperature, pressure, density, pressure, internal energy, density, enthalpy, whatever. Okay, you need at least 2 independent state variables to define a thermodynamic state. There's another calling concept is for this two-phase equilibrium, right? Because for two-phase equilibrium is drawing on these lines, okay? And if you want to determine a location on these lines, actually you only need 1 independent state variable. You do not need 2 anymore, okay? You can determine that the two-phase equilibrium state either by using the temperature, which is called the saturated temperature, or you can just, or using the pressure is called the saturated pressure, or saturated density, saturated enthalpy, internal energy, whatever, This means that for this two-phase equilibrium state, okay, you just need 1 state variable to determine all the others. Okay, this is just some fundamental concept for the two-phase flow. And what about the heat transfer between the phase changes, right? So we know that when phase is changing, right? They either absorb or release heat, right? And also during this process, right? During this phase changing, during this when you have like ice is melting to water or water boiling to the vapor to the steam, during the change of the phase, okay, during this process of phase changing, usually your temperature is not changed, okay, if your surrounding pressure is not changing, okay. And this is one important behavior of the heat transfer during the phase change. And why? Because that in our engineering point of view, okay, sometimes we prefer to do the heat transfer, like if you want to design a heat exchanger, sometimes you want that the fluid inside this heat exchanger has the two-phase phenomenon. Why? Because the advantage of the two-phase heat transfer is that it can transfer a big amount of, a significant amount of heat, without maintaining a large temperature difference. I'm talking like it's a single phase heat transfer. If you want to, increasing the Q dot, right? If you want to increasing the heat transfer rate, sometimes you have to, make sure that the hot flow is very hot and the cold flow is very cold, so that the delta T between them is very large, and so that you can have large heat transfer. But in many engineering condition, right, situation, you cannot maintain a large temperature difference, but you still want to transfer the heat. I'm talking? You cannot maintain a large delta T, but you still want to transfer heat. In that situation, the two-phase heat transfer will become very valuable, because that we know that the two-phase, even there is no heat, there is no temperature difference, you still can have the phase changes and release or absorbing the heat. Okay, so this is why the two-phase heat transfer is very useful in some situation. Okay, and another topic is that why we consider the the two-phase heat transfer as a convection topic. Okay, this is just a pure engineering point of view. Okay, fundamentally, okay, the mechanism of the heat transfer for boiling and condensation is really different with that single-phase natural convection, single-phase convection, either the forced convection or natural convection, right? Because their fundamental mechanism is different. Like the forced convection, like the single-phase convection, the heat transfer is just because of fluid motion plus the fluid conduction. Okay, but for phase changing, okay, phase changing. The heat transfer is just due to, release or absorb of the so-called latent heat, okay. So it's really different mechanism in the fundamentally, but in the engineering point of view, okay, we still consider boiling and condensation as a convection problem. Is really because that in most cases, okay, not in most cases, in all the cases, okay, so when you have the phase changes, it always involve the fluids, okay, it always involve either liquid or gas, and because the heat transfer of the two phase changes, it always involving the motion of the fluid, okay. So although their fundamental heat transfer mechanism is really different, but because of history and because the history of this research, okay, people is still thinking that this is a convection problem, okay. All right. So another topic, another concept that we need to know that is the heat released, right? The amount of heat released during the phase changes. And this Q, okay, is the heat required to do the phase change is equal to M, which is the mass, mass of the fluid, times the H of Fg. And this H of Fg is called the latent heat. Okay, and it has a unit of joule per kilogram. So if you're using M times this unit, you get this Q. The value will be joule. And just another topic, okay, you just want to remind you about your thermodynamic concept, right? You know that the heat transfer is, in thermodynamic view, right? The heat transfer Q actually is the changing of the changes of the internal energy, right? Delta Q equal to U, right? There's another, delta U equal to Q minus W, right? Let me repeat. So delta U equal to Q minus W, right? So this is our from our thermodynamic class, right? Actually, if there's no work, right, you can consider that the changing the heat transfer is just the change of the internal energy, right? And there are two types of internal energy, right? One type of energy is called the sensible energy, right? So this sensible energy is the energy related to the temperature. Okay, so this energy transfer, is because of the temperature difference. So this is what the energy, the thermal energy we transfer during our single phase conduction convection. Okay. Another part of it is called the latent heat, right? And this latent heat usually is related to the, your chemical potential, and also you can thinking that this, and also this is related to the, the heat the latent heat you needed to during the phase changes. Okay, so this is just something like you want to remind you. Okay, where this latent heat is coming from. So this is not, so you can think that this latent heat is not, is different with the sensible energy. Okay, sensible energy means that it's, you can sense it from the temperature. So latent heat is not sensible. Okay, that's why is that when you have the phase changes, the temperature is unchanged. Okay, another concept is so-called the vapor quality. So vapor quality X basically is defined as if you have a equilibrium between mixture of the vapor and liquid. The vapor quality is defined of the the mass of the vapor divided by the mass of total. Okay, and you can also write the mass of total is equal to the mass of vapor plus the mass of liquid. Okay. What does it mean? It means that if X equal to 0, okay, you will means like you have 100% is liquid. Okay, and if X equal to 1, means that you have 100% of vapor. Okay, this is using X. Okay, using the mass fraction. Sometimes people would like to using Y. Okay, another using the molar fraction rather than using the mass fraction to represent the the percentage of the vapor inside the mixture. So that you can see that is not the mass. This is you can call that this y like the molar quality. But in this class, we're just using x. Okay. Talking about this quality things, right? So if we let's do this. Okay. So if we have a curve, let's say we have temperature here, and we have this x location here. Okay. Assume that we have so this is 0, right? And maybe I should not do this. Let me redraw this. Assume that this is time, okay, horizontal time, okay. Let's assume that we have a water, okay, like 20 degree, okay, Celsius degree at the room temperature. At time 0, we try to add the heat to it, right? Okay, so you will see the temperature is increasing, right? And at some point it will reach like so this is like 100 degrees Celsius, okay, at the one atmosphere temperature, 1 atmosphere pressure. So it become boiling, right? And the temperature will not changing, okay, for a period until all the water is converting to the vapor, right? So it will keep increasing. The temperature will rising again, okay. And if you draw for the same process, okay, you draw this 0 to t, okay, and you draw change this y-axis to the x quality, okay. So what you will see? You will see that x equal to 0 and x equal to 1, right? 0 means that everything is liquid. So you in this point, right? Maybe like it's A and this B, okay. So basically you will have like a horizontal when you're heating the liquid initially, if you reach to this A point here, and during the phase changes, this x quality will increasing from 0 to 1 until this B point, okay. And after everything is changing to, to the steam, even you keep heating it, so the quality is, you can still consider it's 1, right? It's not increasing anymore. The 1 is the maximum value of the quality, okay. So this is some correlations of how you're thinking about this quality. And there are another 2 concepts, okay, we usually use for this problem. Between this point A and B, okay, this point here, we call this equilibrium, right? Equilibrium. So this is equilibrium, okay? Some equilibrium, two-phase equilibrium state, because that the phase is changing. And from for this line here, from A here, from this line before the point, before the point A, this curve, we call this if it's heating, okay. Sorry. So if it's let's forget it. If it's heating, okay. If it's heating, consider this point after the B point, okay. This point is called the superheating. Superheating means that if you go this direction, okay, heating, okay. And this point here, or you can see this point is called the superheating. Superheating means that even everything is become gas, but you still add the heat to it, so that it will deviate from the equilibrium state. Okay, but if it's cooling, you consider from the top doing this side, doing this direction, and this location between this location and A, it has a term called the subcooling. Or if you go this direction, this region is called subcooling. This is superheating if you go to heating direction, and this is the heating direction, okay? If you do this one, and this is the cooling direction. And this is called subcooling. Subcooling basically means that even you cool all the steam to the liquid, okay, you still keep cooling it not to make it, departing from the equilibrium state. So this is called subcooling. So that has some concept that what this subcooling and superheating means in the two-phase flow, okay? The last concept that we want to introduce is in the two-phase flow, how we define the heat transfer coefficient, okay? Because it's still, we consider it's convection, right? So we define this H film heat transfer coefficient. So it basically means that, it's defined as that the heat of the boiling. Here I'm using boiling example. This Q dot basically is just Q prime prime in our previous chapter, okay? It's just heat flux, okay? 1 meter square. But in this chapter, I'm just using Q dot. So if you do not like it, you can change it to Q prime. And it will be defined as H times T of S. Okay, because that is, we usually consider of is a solid. Okay, and the liquid. Okay. In this chapter, we're focusing on the boiling and condensation on the interface of the solid and liquid, solid and fluid. Okay, not liquid. Okay, fluid. Okay. So we consider we are focusing on the interface between the solid and the fluid. And in that case, is the heat transfer coefficient. If it's boiling, okay, you add heat from this solid to this fluid to make this fluid boiling. The heat transfer coefficient H times Ts. S is the surface temperature of this wall. Okay, and minus the saturation temperature. Saturation temperature of the fluid, which is determined by the saturation pressure of this fluid. Okay. And H times T surface minus this saturation temperature. So we will come to the heat transfer rate of this boiling process. So this is how we define this H for the boiling. And you can even further write this temperature difference between the surface to the saturation temperature of the fluid to be equal to as the delta T excise. Okay, it's called this is called the excise temperature. Excise temperature. So it's equal to Ts minus T out. Okay, so this is we define how the heat transfer coefficient. And you know that the task, in our heat transfer analysis, right? Our task is usually try to find the Q dot, right? To find that what the heat transfer rate will be. And since you know the surface temperature usually, okay, and you also usually know what the fluid condition will be, the saturation temperature will be, right? So our task is that try to find what is this H value for the boiling different kinds of boiling problems. Okay, so we want to find what this H will be. First, we need to talking about the different kinds of a boiling problem, right? Phenomena. The first thing is that you need to know the difference between the terms evaporation to the boiling. Okay. Actually, evaporation is the happens between the interface of the solid and gas. Okay. Sorry, between the interface of the liquid and the gas. Okay, like you will have a container here, you have water. This evaporation is between this surface here, this interface here. Which in this case is that it's because that usually is because that your vapor pressure. Okay, you are like this air here. Okay, your local pressure, in this air is less than the saturation pressure of the liquid. So the particle, okay, the atoms in your liquid, like to escape from the liquid and go to the gas. Okay, so this kind of thing is called evaporation. This is not what we are focusing on in this chapter. Because I told you we're focusing on the heat transfer between a solid and a fluid interface where you have two phase changes. Where you have phase changes. Okay. So for the boiling will be different. Okay, boiling just means that the phase changes between this solid interface and water, where you add the heat to this solid interface, and this heat causes water, to convert to become vapor. Okay, so this is the difference. Okay, you need to know that what's the difference between the evaporation and the boiling. This is like where it happens is different, and the mechanism is also a little bit different. Okay. Another big difference is the so-called pool boiling and flow boiling. You can think about the pool boiling. It basically means that there is no flow motion here. Okay, it's like you have water in this container, and you just try to add the heat at the bottom of this container, try to boil it. Okay, originally there is no flow motion. Okay, after you add the heat, okay, and you will have natural convection will form here, and the fluid will start into motion. So basically, you can thinking that pool boiling just you know, just like you know, you have boiling in a natural convection case. Okay. And another kind of boiling is called the flow boiling. Flow boiling is just like a, you know, for like you have fluid, you know, flowing inside this pipe, right? And you add the heat on this, you know, on the wall of the pipe. So the phase changes at the pipe's wall will happen, right, to convert this maybe liquid to the gas. Okay. And in this cases, okay, we call it flow boiling because the bulk fluid, and the fluid has a bulk flow velocity. Okay. And you can consider this flow boiling just like a forced convection plus the, you know, plus this pool boiling. Okay. So a pool boiling is more fundamental. Okay, because that it doesn't involve too much of the convection. It only involves the natural convection problem, natural convection plus this boiling here. But the flow boiling is just like you can consider the pool boiling plus the convection. So in another word, is like you can see that you know, if the condition is the same, okay, usually you can saying that the flow boiling will be more effective than the pool boiling, because that flow boiling contains the heat transfer from the pool boiling plus the forced convection. Okay. So this is the two types of pool boiling and flow boiling. There are another type is called the subcooled boiling and saturated boiling. Subcooled boiling basically means that your, you know, major part of your fluid is not to the saturation temperature yet. Okay, but you try to add the bottom, add the heat, and in the region in the fluid, to the fluid close to the bottom wall, they already reach the saturation temperature, but the major part is not reached yet. And when you add the heat here, it's this kind of boiling is called the subcooled boiling. So this is why this is the means of subcooled, right? Subcooled means that you know, is not you know, the major part is still not reached to the equilibrium state yet. And saturated boiling, that basically means that all the fluid, you know, all the fluid is already be at the saturation temperature already. Okay, and you just add the heat, so it will be coming to boiling directly. So this is just some, you know, classification of the different type of the boiling. And so we will go through each types of boiling. Okay, so we will first introducing the pool boiling. Okay, and then we will go to the flow boiling. Let's first talking about the pool boiling. Okay, and pool boiling, the thing is you need to realize is that the complicated you know, physical phenomena involved in this pool boiling process. Okay, think about that you have water in this container and you try to heat it until it boils. Okay, and look at this picture. Okay, if you have this, consider that this x-axis is this excess temperature. So which means that you know, the surface temperature minus saturation temperature, right? Think about that you keep increasing this surface temperature, right? From at this point you try to keep increasing the surface temperature, and what the heat transfer rate will be. Okay, and if you're showing that if you keep, you know, you're increasing this when you try to boil water, right, or boil other liquids, and when you try to increase the surface temperature of your heated surface, the flow will, you know, go through different flow regimes. Okay, in the beginning, okay, if you just you know, if you in the beginning, you know, if your flow, if your water is 20 degrees, right, and you just try to starting to heat it, and in the beginning, from this point to A, okay, you won't have a two-phase exchange happens yet. Okay, because it's not a, you know, maybe the flow is not the you know, the bubble, okay, the gas bubble is not formed yet, okay, due to the phase changes. And this region is called the natural convection region. Okay, natural convection boiling. Why? Because natural convection boiling means that in this region, because everything is still liquid, and when you try to add the heat on the bottom, so this is just natural convection problem, single phase natural convection problem we had before, right? Like you heated at the bottom. or for convection in a container, right? So in this region, okay, it's called the nitro convection volume, which means that just the dominated heat transfer mechanism is the nitro convection. Okay, and at this point of A, okay, you will starting to have the bubble created. Okay, or you can see that in bubble can be observed in various nucleation position. Okay, location, nucleated location, and this point of A has a term is called the onset of nucleate boiling. Means that at this point the nucleate boiling happens. Okay, or you can call it ONB. Okay, so which means that at this point, if you try to keep if you try to still increase the surface temperature on the bottom, your bubbles will starting to form at the bottom. Okay, and so in these cases, okay, the bubble is still very small. It's in the beginning of this condition, right? When it's close to the A, you have very few bubble created. But if you try to keep at your temperature at the bottom, right, surface temperature, I don't know, your more bubble will be formed. Okay, and one thing you need to know is that usually the liquid, right, has a much higher thermal conductivity than the gas, right? And so that means that if you have the same temperature difference, more heat will transfer by liquid rather than gas. Okay, that's why is that usually sometimes we consider the gas can be some kind of insulator. Okay, insulated material. Okay, so in the beginning of this nucleation, in the beginning where the bubble is created, right? Because the bubble is still very small, the number of bubbles, and the major part of where the contact with the bottom, right? The major liquid, the major fluid contact with the bottom heated surface is still liquid. Okay, and but because the creation of the bubble, right? You have the bubble, and then bubble will try to move up, right? Because the bubble has a lower density, and this bubble will try to stir your fluid, right? You have the bubble will try to stir the fluid because bubble want to move up. And this is the additional motion caused by this bubble, okay, will actually increase the heat transfer rate, because that although many of them is still the liquid, right? This bubble cause some motion of the liquid, okay. That's why is that you see the heat transfer is still increasing at A to this point of B, okay. This region between A to B is called the isolated bubble, okay. But after this point of B, okay, if you still try to increasing the surface temperature at the bottom, more and more bubble will be created, and at some point, okay, the fluid contact with the bottom surface will be more bubble rather than liquid, and because we know that the bubble has lower thermal conductivity, right? So actually is that if you have a lot of bubble at the bottom, right, you have fewer liquid can contact with the surface. So that means that it's not like you create more bubble actually will increase will help to increase the heat transfer rate. You create more bubble at the bottom, and it will actually try to reduce the rate of the heat transfer at some extent. Okay, so that's why that after this point B, that is although it's still increasing, right? Because that this bubble is still bring the velocity of the fluid, causing the natural convection, or and making the fluid moving to increase the the heat transfer of the liquid between and the surface, solid surface. But because you have more bubbles, and actually you reduce the heat transfer area between the liquid and solid, so you will see that the rate actually will not increase as fast as before. Okay, it will eventually this slope, the increase of the slope actually will eventually reduce. Okay, so at this point B and C region, we will see that this region is called the continuous columns of liquid, which means that you have a lot of bubbles. It's just like a, continuous, columns of gas, vapor, from the bottom to the top. Okay, so this is in the region B to C. Okay, and eventually we'll reach to a maximum point at point C, and this point C where you will have the maximum heat transfer rate. Okay, because that the combination of these two, the bubbles effect and the liquid transfer. Okay, liquid heat transfer, and this maximum heat flux Qmax has a term called the critical heat flux. Okay, so basically between this region A and C, we call this is called nucleate boiling. Okay, and inside this nucleate boiling, we have two regions. One region is A to B, we call it isolated bubbles, and another region B to C, we call it to continuous columns of liquid. Okay, and after you reach to this maximum point value C, if you still try to increase the temperature of your heated surface, that's what will happen. What will happen is that the flow will go into the so-called transition boiling. Okay, transition boiling means that is a transition region between this nucleate boiling and another region called the film boiling. Okay, and basically it means that you have a lot of gas formed. Okay, and in the film boiling, which means that you will have like at the bottom, right? In the film boiling basically means in this region. Okay, let me draw it. If you heat it, right? Q dot I heat it. Like you will have a thin film at the bottom. All this thin film is vapor, and the liquid is on the top. Okay, so basically you will form a small film of vapor. Okay, and we know that vapor is behave like an insulation, right? Because vapor's thermal conductivity is much smaller than the liquid. So that's why it's very small in the beginning. Okay, the Q dot actually will reduce. Okay, let me also draw it. So in this region is pure convection, right? So that's like the flow is coming to this, flow coming to this. And in this nucleate boiling, in this region, okay, it's just like you have small bubbles going up. And in this region, it's like you have a column large bubble going up. Okay, going up. And in this region is like you have it's called film boiling, like you have a thin film of vapor forming at the bottom, and you have the bubble from here going up, bubble from here going up. Okay, and the transition region, that's like you can consider that the transition between the nucleate boiling and film boiling. Okay, and at this point D, where you will have the minimum heat transfer rate, Q min. This minimum heat transfer rate is like you in the beginning where you're starting to form this vapor film, and this point, okay, is a term called the latent flows point. Okay, so you have these 2 points here. So we have film boiling, beyond the D point. So this is the whole boiling curve, right? I don't know. I think a lot of you maybe already learned this before. Okay. So what's the ideal cases? Okay, in the heat transfer, we usually always want to have the maximum heat transfer, right? So actually, the ideal operation condition is that we try to maintain the boiling close to this Q dot max, right? Because we want to have the maximum heat transfer rate, which means that we prefer, okay, in our engineering problem, we prefer the nucleate boiling, okay, but in the region close to the Q max. And the transition boiling is usually considered as an unsteady region, which means that it's hard to control. Okay, if you're using this region, maybe you will suddenly moving to the left or suddenly moving to the right. So in the applicable, the best applicable condition is that in the nucleate boiling, where you have close where your condition is close to this critical point. Now, this is what we want. All right. And another thing is so-called another behavior we want to introduce is the so-called burnout phenomenon, right? The burnout phenomenon is also for this curve, but remember that for this curve, when I introduce this boiling curve, I think that on this x-axis, right? I try to keep continuously increasing this surface temperature Ts, right? So that's why you will have this continuous curve here. But in some application, okay, it's not like we can control the surface temperature, but we can only control the heat transfer, heat flux at the wall, okay. This is actually is like we can control it not from this horizontal location direction. We try to control on this y direction. Okay, we try to increase the heat flux eventually rather than increase the surface temperature. So in that case, what will happen? If you do the boiling, right? If you boiling from this in this direction, if you try to increasing the heat flux, after you reach to this point of C where you have the maximum heat flux, and if you want to continue increasing the heat flux, wall heat flux, what will happen is like it will suddenly from this C point, it will directly go into this E point, moving horizontally, okay? They call a suddenly jump in temperature to here, to this point, which means that because this is directly excites, right, at this E point, that means that you will have big jump, okay? If you keep increasing this surface, if you increase this your wall, heat flux is larger than this critical point value, you will observe a sudden jump in temperature because this direction is a sudden jump of the temperature, okay, surface temperature, and the surface temperature at this point E value will usually become very large and usually will burn your container, okay, your container will just be burned out, okay, so that is the so-called burnout phenomenon. So you need to be careful about these things. And similar things, if you try to cooling down, right? Not the boiling, try to cooling down. If you're using this wall heat flux to control, okay, not the temperature, surface temperature to control. And after you control to the minimum value of D, you will also correspondingly has a sudden temperature drop, to a location on this curve, okay. So this kind of phenomena is called the burnout phenomena for the boiling, okay. So we need to avoid that. So as I said, okay, as the ideal case, okay, is make the boiling in the nucleate boiling region and regime where close to the Q dot max. This is usually the best condition we want. Okay, so all the previous we talking is this boiling curve is descriptive, talking about this boiling process, right? So we need to go back to the heat transfer rate, and let's first, we do not need to consider this region, right? Because this is the natural convection region in this natural convection boiling. So, we do not need to consider it. We already learned it in our natural convection chapter. And so we were focusing on this region, nucleate boiling, this region here, because this is where the most applicable condition we use in the engineering. And, we also talking about a little bit about the film boiling. And the transition boiling that you can consider is some transition between these two. So you can just using some interpolation method, to interpolate between this point and to this point here. Okay. So let's first looking about the heat transfer in the nucleate boiling. For the boiling problem, we do not have any analytical solution. Okay. In this class we focusing on the analytical solution, but for this nucleate boiling, we do not have any analytical solution for it. And so we will go to the empirical. So this is one of the most used empirical correlations where you can calculate the, the heat transfer rate of the boiling, nucleate boiling problem. It's called the rational correlation, and it's defined as this term. Okay. So the meaning of each variable is given. So this small l here, okay, means that for the liquid phase, okay. So mu of L is the liquid phase viscosity. So if I write mu of V, okay, small v, that means that the vapor phase of the viscosity, okay, so it's different. HFG is latent heat or vaporization, okay, and this G is gravity. Because we have in this nucleate boiling, we have this natural convection involved, so we will have this gravity inside, and this rho of L is the density of the liquid, and rho of V means the density of vapor, because this is different. Okay, and this sigma here is the surface tension between the liquid and vapor interface. Sigma is the surface tension. CPL is the specific heat at the constant pressure for the liquid, and TS is surface temperature. TSAT is the saturated temperature of the liquid. And this Prandtl number R, it means that this is the Prandtl number for liquid. You will also have this a constant of CSF here, and another constant N here. Okay, so these two constants is determined by the, for the CSF. Okay, this constant is all these two constants is determined by the experiments. Okay, and you know, CS value will relate it to the combination of the surface fluid. Okay, surface fluid combination, and this N usually is determined by the fluid. And you will have a table. Okay, you can find, this is not a complete table, it's just some example. Okay, you can find the complete table on your textbook. Okay, for more combination of the liquid and surface. Okay, and for more fluids. Okay, to find all what's the value for CSF and what's the value for N. So if you bring this CS value and N from which fluid you use, which is the solid surface you use, you can immediately calculate the nucleate boiling heat transfer rate. Okay, so this is the correlation we can use for nucleate boiling. Definitely, this is not the only one. Okay, if you do a literature review, okay, you can find many, you know, many correlations for nucleate boiling. Okay, and some they may working for different type of fluids. You know, they may will even working for, you know, different type of you know, conditions. Okay, so so this is just one of the, you know, representative correlations we're showing here. Okay, because this is more this correlation is the most, you know, famous one. Okay, so this is the one correlation we can use for the nucleate boiling. And the second correlation is also empirical. Okay, is that how we can determine that the critical point, where this Q dot max will be, right? The maximum heat transfer rate. It's from an empirical correlation divided by this Zuber. And so you're seeing that, you know, it calculates this constant of this CCR, critical constant, times this H of FG, latent heat, times sigma is the surface tension, times gravity, rho of V is the vapor density, rho of L is the liquid density. Okay, this is an empirical correlation. And this constant is given at 0.149. Okay, so this is an empirical correlation. You can find that what this Q dot max will be at this point. Similarly, we will, the same guy, okay, develop another correlation, empirical correlation that you can determine that latent flow point where you have the Q dot mean. Okay, the minimum heat transfer rate, where, you know, the starting of the film boiling. Similar things. Okay, this rho V is vapor density, rho L liquid density, sigma is surface tension, and H of FG is the latent heat. Okay, so this is another two empirical correlation you can use to determine the Q dot max and Q dot mean. And for the last one we want to talking about is the film boiling. The film boiling is you know, the boiling on this part, right? On this region, where you are seeing that you form a small film of vapor at the bottom, so that no liquid to contact with the bottom surface directly. And in this case, there is another empirical correlation available for the film boiling on a horizontal cylinder or sphere. So this is just some example here. Okay, and as I told you, if you do you know, if you study your literature, right, there are many of these correlations. Okay, so that means that this is not the only one. Okay, you have, even for the same problem, different researcher, you know, they do experiments and they give you the different empirical correlations. And even these days, okay, it's the new published paper, people is still try to publish more the new correlations for this kind of boiling empirical Bowling correlations in these days. Okay, so this is the thing how you can calculate the heat transfer rate for the nucleate Bowling, for the pool Bowling. And another thing is the flow Bowling, right? After you finish the pool Bowling, it's the flow Bowling. Flow Bowling is usually happens that in two cases, right? Determined by your flow motion. One is called the external flow Bowling, which means that your flow Bowling, your flow, okay, is the external flow cases, like this in these cases, right? If you have a tube here, but the flow is not a flow inside the tube, flow is across this tube, okay? So the Bowling will happen on this outer surface of this tube, okay? So this is called the external flow Bowling. Or you may have the internal flow Bowling, which means that the flow is flow inside the tube, and the inner phase, the tube has a higher temperature, so that the Bowling happens on the inner surfaces of the tube where the Bowling happens. Okay, so this is called the internal tube Bowling. Okay, as I told you that you really can't consider the flow Bowling just basically including the two part, right? The flow convection plus the pool Bowling. Okay, so the heat transfer contribute from this flow convection, and plus the the two phase changes. Okay, so pool Bowling plus pool, and there are also many empirical correlations. Okay, for the pool Bowling, for this flow Bowling, and most of this a large portion of this empirical correlations. Okay, you can see in that okay, in those equations you find that the h of the flow Bowling will be in a form of this some kind of function of h of single phase convection plus h of pool Bowling, not h, okay, dot, okay, another pool Bowling. Okay, so if you do your literature search, okay, want to find that in these cases you like to flow inside the tube. Okay, if you have a flow Bowling, how to calculate this H coefficient? Some correlation may be just saying that this H flow of Bowling will be equal to like 1/2 of this H of convection C1V square plus this H of pool Bowling square. And this convection square you can just using your single phase for liquid problem, because as I told you, do not use the vapor, okay? Because vapor do not transfer a lot of heat, okay? In the liquid cases, like you find that what's the quality, right? Like the quality is x, okay? 1 minus x times m is the number of your quality, the mass flow rate for the liquid, and then times that heat transfer rate for using this liquid one, you determine the Reynolds number of liquid, right? And using the Reynolds number of liquid, you're using that the correlation that we had before for forced convection. For laminar flow, it's like Nussbaum number is 16 over Reynolds number, right? No, not 16. The Nussbaum number is 3.1 something. I forgot. Okay, 146 or something. You can calculate the heat transfer rate for this liquid part, right? And if it's turbulence, you can using the Beatles boilers, right, to calculate the heat transfer rate for the convection liquid part of convection single phase. And then for the pool Bowling point, you can just using the correlation we just introduced here, right? This you can using the rational or other pool Bowling correlations for this part, and then they combine it to consider as the flow Bowling. So this is the one type I saw before. Some people use, some paper use, some other even making this 3, this 3, and this 1/3, and someone even using more complicated correlations, but with some correction factor that which is determined by the experiments. Okay, so this is just usually like how people handling the flow Bowling. Like they just consider it as two parts. One part is a single phase liquid convection, another part is pool Bowling, and they try to combine these two parts with some constant modified constant, which can be determined by the experiments. Okay, so I won't give you any example of them. Okay, but if you later on, if you want to do some research or do some experiments and you want to estimate it, you can go to this literature. You can find a lot of this kind of equation. Okay, how to calculate the heat transfer coefficient, for the flow body. Okay, so here we finished talking about the body, and we will move to the second part of the condensation. Okay, any question, guys? Okay, no question. Condensation is more. Okay, so flow. Oh, I forgot about talking about the flow regimes for the flow volume, internal flow volume. Okay. So for the flow, if your flow is inside, okay, the tubes is internal flow volume. Actually, you will also have different flow regimes. Okay, for the, for this internal flow volume, and this regime is determined by your local quality. Okay, in the original, like your quality is 0, everything is liquid. You have the pure forced convection, right, for the liquid, and when you're increasing the, when the flow keep moving, right, and it receive more heat, from the wall, and the bubble is formed at the region close to the wall, and you will have the so-called bubbly flow. And if you're still going downstream and more heat added, okay, and these bubbles will, form this, big slug of the bubbles, okay, and they call this slug flow region, and continually you will see that we go to the so-called annular flow. Annular flow means that you have like a boundary, you have small films of the vapor formed around the wall, okay, close to the wall, and in the middle you will have a core, and that is fluid, is liquid, okay. Like the annular flow means that you have the vapor around the wall and the liquid in the middle, okay. If you're that's going on, okay, you can be to the mist flow, which means that so this is so the pure liquid region is almost done, not seen anymore, okay. It's like everything is like the mist, very small particles of the liquid inside the vapor. And even if you're just going downstream, keep heated, all the liquid droplets will become the vapor. Everything is vapor, so it becomes the forced convection again. But this forced convection is for the vapor, and on the bottom is forced convection for the liquid. Is different. Okay, so and if you look in the heat transfer rate, okay, during these phase changes, it's like if you increasing with this quality originally and reach to a maximum point at some point, and because and then it will reduce suddenly because that you have this more vapor than the liquid created, okay, and eventually at the end. So this is just some flow regime consideration, okay. Okay, so now we move into the condensation. Actually, condensation problem is more, if you read the convection book, actually, most times the condensation problem is more, discussed, okay. The reason is because that, like you see what we have, what we go through for the boiling problem, right? The boiling problem, we won't have any analytical method, analysis for the boiling problem. Most, those correlations is from the experiments, is the empirical correlation that we use, okay. But for the condensation is different, okay. And the condensation, we do have some kind of analytical solution available. Okay, no, of course you need to do some assumption to simplify the problem. Okay, and that's why is that the condensation is more, usually for this convection book, you'll see like a larger, bigger chapter, more detailed derivation, more things to discuss in the condensation. Okay. Let's first also think about the something we want to introduce, right? Condensation can happen in many places, right? But in this chapter, we're only focusing on the condensation at the interface of the solid, as a solid surface. Okay, we can also have the condensation, between the vapor to the fluid, right? But in this chapter, we didn't discuss that part. We consider the condensation of the vapor on a cold solid surface. Okay. And once your surface temperature, right, is lower than your vapor's saturation temperature, you have the liquid, formed on the surface of the solid, right? So the condensation happens. There are two types of condensation. Okay, we usually have. One type is called film condensation. Okay, which means that you like in this picture here. Okay, it means that we have a solid surface here on the left, and this surface has a temperature lower than the saturation vapor. Okay, saturated vapor temperature. And so vapor will have the liquid will form on these cold surfaces, right? And it will form a thin film of liquid film. Okay, and this film will, and because the gravity, right? If you have gravity on this direction, so the flow will moving down. Okay, and so this film will keep developing. So this film thickness will keep developing. Why? Because that when it is falling down, more and more vapor is converting to the liquid. So the mass flow rate in this film is not constant; it keeps increasing. Okay, m dot. So it's falling down. So this kind of thing is called film condensation. Another type of condensation is called dropwise condensation. It's just like you have solid surfaces, and you have those isolated, droplet, formed on this surface due to the condensation. And this droplet is, keep increasing, okay? And when it is increasing to some size, you will just try to move going down, okay? Because it's more, more vapor is condensed to the liquid. So this droplet will increasing with time, but it will, after it's large enough, so so that the friction cannot overcome the gravity, this droplet will just falling down. Okay, and if you compare these two, okay, for this film condensation, right? Because we want to transfer the heat between these solid surfaces with the vapor directly, right? But if you form a liquid film, so like you have an additional things in the middle of the solid surface and the vapor. That's why we're thinking that this liquid film behaves like an additional, resistance to the heat transfer, because that you add a new liquid layer in the middle between the surfaces and the vapor. Okay, and for the dropwise condensation is more simple. It's because that the vapor can directly contact with the solid surfaces. So there's no that additional liquid film in the middle, no additional thermal resistance in the middle. So that's why is that usually speaking, okay, the heat transfer rate of the dropwise condensation is usually larger than the heat transfer rate of the film condensation. Okay, sometimes you can see that it's more like 10 times of the film condensation, the heat transfer rate. Okay, for the dropwise condensation, and comparing to the film condensation. Okay, so we will looking at these two type of condensation. Okay, for the film condensation, okay, we will study it with some analytical procedure. Okay, because the analytical solution is available for this one, film condensation. For the dropwise condensation, we don't have any analytical solution for it. So we will still, people use these days, people will still study it using the empirical way. Okay, try to give the empirical correlations for it. Okay, so let's talk about the film condensation. Okay, the most typical problem of the film condensation is the film condensation on a vertical plate, okay? Like you have a cold plate, okay, vertical plate, and you have a vapor here, and because the temperature of the surface is lower than the saturation temperature of this vapor, so you have this liquid film form, okay? So let's define the coordinate, right? The x coordinate is still, the direction along the surface of the plate, and the y direction is perpendicular to the plate direction, okay? And let's still assume that is delta, okay? As the delta here is delta, as this is the thickness of this film, and we will have a mass flow rate m dot, okay, for all the liquid inside this film, and this m dot is not a constant. It's because it is increasing with this x location, because that when it moves to downstream, more and more vapor is condensed to the liquid inside. Okay, that's why that this liquid film is keep developing, because more liquid is coming in. Okay, if you're looking about the temperature profile, okay, this is a typical temperature profile. At the very left, and the temperature will be surface temperature, and it will increasing. And at this boundary layer point, okay, not layer, film boundary point. We do not call this boundary layer, okay? We call this film boundary. At this film boundary point, the temperature will become the saturation temperature, okay? And in this case, we have some overheating, okay? Which means that the fluid is in the T infinity free stream, which is larger, a little bit larger than T SAT, the saturation temperature. So we have in this plot, we have some kind of overheating. So after the after this y go beyond this boundary thickness, the temperature is still increasing from this saturation temperature and eventually reach to the free stream temperature, overheated temperature of the vapor. Okay, this is the typical temperature distribution. And if you're looking at the velocity distribution, okay, at the left at the wall, this liquid has no velocity, right, at the surface, and because gravity, right? So this liquid will moving, will gain the velocity going down, right, and reach to a maximum value, and at the boundary, right, at this film boundary, you will also have this liquid surfaces will also have a liquid surface will also has a velocity, okay? This liquid film has a velocity, and because the viscous between the liquid film and the vapor, okay, the vapor close to the this liquid film will also have some velocity due to the viscous effect, and then eventually this velocity will reduce to 0 in the region very far away from the plate. Okay, so this is the vertical. So this is a typical structure of the typical velocity distribution in this film condensation. Okay, and we also have the different flow regimes. Okay, for this one, because the flow inside the liquid flow, okay, inside this film can be either laminar or turbulent. Okay, and again, okay, it's also determined by a Reynolds number. Okay, and to define this Reynolds number, first, let's to define the hydraulic diameter for this problem. Okay, so if you're looking at this film, okay, on this liquid film on this plate, from the top to the bottom, so you will have like some view like this one, okay. So it's from top bottom. So this horizontal is like this horizontal distance you can consider like a unit width on this direction here, okay. On the bottom, if you know that we define the hydraulic diameter as a 4 cross-sectional area divided by the weighted parameter. Okay, so this P must be weighted parameter. Okay, so you're looking at this film region, right? This is delta, right? This is the thickness of this liquid. Okay, and if this area cross-sectional area of all this liquid region will be just, if you consider this is 1, okay, unit width of this liquid. So it will be delta times 1 will be the same. So on the top will be 4 times delta times 1. And if you look at the parameter, right, parameter of the YT parameter, so the whole parameter will be this one, right? But the YT parameter is that it's only this region, because it is only this surface is, you know, is YT. This is the contaction where the liquid contact with the solid. So the YT surfaces is only this region, so it's only the 1, okay? Not this 1 plus 1 plus delta. No, it's only this one. It's only this surface is YT. So the hydraulic diameter overall, okay, if you do this one calculation, you'll see the hydraulic diameter, the local hydraulic diameter, okay? And because this delta is keep changing, right, on this x direction. But at any x location, you will have hydraulic diameter equal to 4 delta. Okay. And so based on this 4 delta as hydraulic diameter, you can define a local Reynolds number using this length scale, hydraulic diameter as length scale. It will be 4 delta times for rho for L, because everything in this film is liquid, right? Times rho L times UM, mean is the UM is the mean velocity, okay, and divided by mu L, the viscosity of the liquid. Okay, so by this definition of the Reynolds number, you can separate the flow into 3 regimes. Okay, usually speaking, like when Reynolds number is smaller than 30, local Reynolds number is smaller than 30. In this region, we consider the flow is laminar. Okay, and if the Reynolds number is larger than 1800, okay, we consider the flow is fully turbulent. Okay, and between 30 and 1800 is like the transition between the laminar to turbulence, right? We call this VV flow regime. The VV means that you know, the boundary layer, this not boundary layer, this film boundary, you will see some periodic ripples. Okay, but with some, you know, it's organized. Okay, it's not chaotic. Okay, this ripples. Okay, so that's the reason we call it the VV regimes. But after it becomes turbulence, so this will not become chaotic. Okay, this boundary. Okay. So this is how we determine different flow regimes for this filmed condensation on a vertical plate. So we will study the heat transfer behavior for these 3 flow regimes, right? Okay. You know, heat transfer rate if the flow is in the laminar regime, heat transfer rate if the flow is in the VV flow regime, and the heat transfer rate if this condensation, film condensation, is in the turbulent flow regime. Okay, more focus is on the laminar flow regime, because that because there is an analytical solution available, and this analytical solution is called the Nusselt's analysis of the film condensation. Okay, this is a very few analytical solution available for the 2-phase problems. Okay, so is laminar. Okay, and we do a lot of assumptions. Okay, many assumptions. First thing is that we assume the flow in the liquid film is laminar and you know, is constant properties. Okay, because that even though you know, we have the temperature changes. Okay, we consider the liquid is no thermal physical property is constant. The second thing is that you know, we neglect the overheating on the vapor region, right? As I told you, we still have this overheating from the saturation temperature to this free stream temperature. We neglect this overheating region. We just considering that the vapor reservoir is at a rest, no velocity, and everywhere is this vapor is saturation temperature. So everything here is saturation temperature. Okay, and we also assume that the acceleration of the condensate layer is neglectable. If you're looking at the velocity, right, for this liquid, right, because the gravity effect, right? Your gravity is usually larger than the wall friction, right? So it's like a on this side, if you're going further downstream, actually the mean velocity will keep increasing. Okay, because more liquid is going in, right? So this flow will become faster and faster going down. So we just neglect this acceleration effect. Just assume that the viscous force is equivalent with the gravity force and the pressure force, and also the additional the additional gravity force coming through the condensation, more the liquid added in. Okay, so this is another assumption we made, and the next assumption we made is that at the so the temperature profile, okay, we assume a linear distribution. Try to make the problem simple. At the wall is equal to Ts, okay, and as this surfaces, as this boundary, film boundary, the temperature will become to the T saturation. Okay, so that means that the temp inside this liquid film layer, the temperature varies linearly from the Ts at the wall to the T saturation at the y equal to delta, right, which is the boundary. Okay, and so another simplification we made is that we assume that there is no shear friction force, okay, between the vapor and this liquid film. Okay, so basically means that if you're looking at this velocity distribution, right, at this point, right, so we still have gravity, we still have this slope here, right, at this point, that U slope, because that we have the shear force due to the friction between the vapor and the liquid. We assume that the vapor, their mu is too small, okay, it can be neglectable, okay, there's no shear force. So in that cases, if you draw the velocity distribution, okay, you will see then that at this point, at the boundary, there's no gradient, velocity gradient anymore, okay. So so this curve become horizontal here, okay. So basically partial u, partial y at y equal to delta equal to 0. So this is another assumption we made. And the last assumption made is for just assume that across this is liquid, this is vapor, right? If you consider the pressure drop on this x direction, okay, so if you're jumping from this range to this region to this region, jumping from the liquid to the vapor region on this y direction, right? The pressure changes in this y direction across the film is neglectable. Basically means that if you have a point on the left of the film, this boundary, you calculate this pressure drop on this x direction dp dx will be equal to the dp dx at the vapor region. Okay, dp dx at the vapor region on the right of the boundary layer. Okay, so this is some many assumptions we made for this no set analysis of film condensation. Okay. So let's starting from the momentum balance, right? The force balance, because that with this assumption number 3, right? We think that there's no acceleration for the condensation layer, right? That means that the force, okay, on control volume on this x direction has to be balanced. Otherwise, it will have acceleration, right? If the summation of the force is 0, then there's no acceleration. So let's first define a control volume on this region. So this is the control volume will be, okay? And assume that the control volume is starting from this y to the delta on the y location. And on the x direction, you have like small delta x here, okay? So if you look in this control volume region, you will have pressure force on the top and the pressure force on the bottom. You will have the friction on the left, and you will also have the gravity, for the whole control volume. Okay, and on the right, they do not have the friction because we assume that there is no friction at the boundary, right? There's no shear on the boundary. So if you do force balance. So the G is the gravity, and dm is basically the mass flow, the mass of the whole of the liquid inside this whole control volume, right? So dm will be the density, liquid density times the volume, which will be this length times this length, right? And it will be delta minus y. Delta minus y is this location, this length here, times this dx. So this is dm. Okay, G times dm is the gravity force. Okay, it's going down, right? And minus the friction force, right? Friction force is from the liquid viscosity. So friction force is equal to minus mu L, liquid viscosity times the partial U partial Y. Okay, is visible, and times this surface length times dx. So this is the viscous force. And also you have the pressure force, right? Pressure on the top, on the bottom. So the net pressure force will be just minus dp dx times dx, and times this also times this surface length, which will be y delta minus y. Okay, so all these three forces need to be balanced. Okay, and also that you have this dp dx term, right? Remember that we have assumption saying that the last assumption saying that the pressure changes on x direction, you know, on y direction across the film is the same. So that means that this dp dx on this liquid region is the same as dp dx on the vapor region. And if you do a vapor region x momentum equation, you'll get this one: dp dx equal to rho v times g, because there is no fluid motion. So in the vapor region, the pressure drop is just equal to the gravity. So you can also just change this dp dx in the liquid part with this rho v times g. V means vapor. Okay. You add this, you bring this mass flow rate, dp dx term to this force balance. Okay, this will be your final result. Viscosity equal to the gravity, corresponding to the density changes from the liquid to the vapor. Okay. We integrate this equation on y from y equal to 0 to delta. Okay, and also remember that at y equal to 0 at this location, there's no velocity, right? So after you're doing that, because the reason you can do this is that because this delta is only a function of x, okay, it's not a function of y. So you can just do integration directly. This will be the result. Your u velocity will become to rho l minus rho v divided by mu l times gravity and times this quadratic term. Okay. With this velocity, okay, you can also calculate the mass flow rate. What's the overall mass flow rate at this location, right? At this x location. First, let's consider the mass flow rate per unit width of the plate at this x location. So basically, you just need to integrate from 0 to delta, right? At this x location, what the mass flow rate will be? You integrate from 0 to delta times rho L liquid density times this u velocity for dy. Okay, and you bring this u distribution to this equation here, and you get your this gamma, right? What's the mass flow rate, at this location will be? So it will rho L times rho L minus rho V times G times delta cubic divided by 3 mu L. Okay. So you will also have the mass flow rate here. And now we are knowing that this mass flow rate, right, is increasing with the active action, right? I told you, we discussed this, that when this liquid film developing going down, more and more vapor is converted to the liquid, so that this mass flow rate will increasing. And what's the rate of this increasing? You can do it by using this mass conservation in control volume. Okay, consider you have control volume from x to x plus dx. Okay, and then you have this gamma is will changing to gamma plus dT or dx to dx. And the changes is that how many vapor mass is converted to the liquid. So which means that you have this D of m dot v, okay, and this m dot v means vapor, okay. You will be equal to the, gamma plus d gamma dx times dx minus gamma for this balance, right? And so that we know that, okay, this how my this relationship between the mass flow rate of the liquid and the rate of how many vapor will be converted, the mass rate of the vapor converted to the liquid. Okay, m dot. So we have this relationship here. Okay, so this is velocity and hydraulic analysis, right? So now we will go to the thermal analysis. Because our ultimate goal is want to see that what the heat transfer coefficient H will be for this case. So to do that, let's make the simple cases, okay? First, let's neglect the subcooling effects. So what does this mean? So if you look in the heat transfer rate between the plate and the vapor, right? We know that at this boundary, right, the vapor will be converted to the liquid. Okay, so then which means that it will release, the vapor will release the heat transfer rate due to the latent heat, right? And also, because in the region inside of this liquid film, because this temperature gradient, we will also have the additional heat transfer due to this temperature gradient, right? Because that the wall temperature is much smaller than the saturation temperature. So this region is called the subcooling region, right? We're seeing because that is subcooling. So the heat transfer rate, finally, the heat transfer rate they received at this location will be equal to the latent heat released at the boundary here, and also because that this is a gradient, temperature gradient due to the convection. Okay, so the first case is which means that we neglect this heat transfer rate due to this convection, this temperature gradient in this region, and that's assume that the heat transfer rate at this here is just equal to the latent heat when the vapor is converted to the liquid. Okay, so this is the first cases. Okay, we just neglect the subcooling effects and assume the cooling of the liquid below the saturation temperature of the liquid in the condensed film is very small. Okay, the subcooling, and compared to the release the latent heat. Okay, so what's the heat transfer rate at the wall? Because this is we assume a linear distribution of the temperature. So it can be immediately given that this Q dot X will be equal to the K of L, the liquid thermal conductivity, times the gradient of temperature, right? Because it's a linear profile, it will be T saturation minus the T of surface and divided by this thickness of the film delta. Okay. And also because that we assume that this heat transfer rate is just equal to the latent heat, right? Because we neglect the subcooling effect. So you can also write in another word from the two-phase view. You can also write this Q dot X equal to latent heat HFG times this D m dot V, okay? Which means that the rate of the vapor converted to the liquid. And remember that we already developed the correlation, right? This D m dot V will be equal to D gamma or dx, and this gamma is also given here. Okay, so you submit you substitute this dm dot v vapor with that gamma correlation, and this gamma is given as this one. Okay, and so because you need to these two is same, right? Because they are all go to Q dot X. So this one will be equal to this one, and you're converting. So this is gamma, not T. Okay, let's make it bigger. So this is gamma, not T. And you bring the gamma correlation that's inside. Okay, you have this equation here. Okay, and you're looking at this equation, final equation. Okay, you're seeing that all this HFG, rho L, rho V, mu L, KL, TSA, TTS, they are all constants. Okay, and only the delta itself, the thickness of the film layer thickness delta is a function of X. So you will have an ODE for delta to solve. Okay, you just need to solve this from this equation. You can directly solve what delta it will be. Just do integration on both sides on x. Okay, and also knowing that knowing the initial condition that at x equals 0, your delta equal to 0. Okay, so with this boundary condition at x equal to 0, this delta will also be 0 here at t. So you get your film boundary, film, the thickness of your film layer, okay, this delta. And you will see that actually this delta is proportional to this x location to the power of 1/4. I'm saying delta is proportional to x of 1/4 in these cases. Okay, this liquid film thickness. Okay, after you solve this delta, okay, you bring this delta back to this. You bring this delta back to this correlation here. Okay, because delta equal to this KLTS, right? Just substitute this delta to this one. You will know that what the heat transfer rate will be. Okay, the heat transfer rate will be Q dot X just equal to this value. Okay, and you define the heat transfer coefficient with this one. This is for condensation, right? For boiling, we have the similar thing that we introduced before. Okay, so you can see that this heat transfer coefficient just rearrange using this one divided by this one. Okay, if we get heat transfer coefficient, H will be become to this value. Okay, and after you have this heat transfer coefficient, you can define the local Nussbaum number, which will be H times X divided by K of L. Liquid thermal conductivity will be this complicated result. Okay, and after you have the local one, you can calculate the mean one, right? The mean one, basically you calculate the mean heat transfer rate and then calculate the mean H bar. And so you can define the mean Nussbaum number. So you will have the final result, the mean in this laminar film condensation, around on a vertical plate. If you using Nussbaum analysis, this is the final result. The average Nussbaum number will be equal to 0.943 times this constant here. Okay, so this is the procedure that this Nussbaum analysis of how you can derive analytical solution of what the local H, local Nussbaum number, and the mean H and mean Nussbaum number will be. So this is the result. Okay, this is an analytical solution for you. Okay, any question here? So actually this part is important, okay, because it's analytical solution. So if you you need to prepare for the qualified exam, so this is some part you really need to be aware of, okay, because the qualified exam they won't test your empirical correlation, right? They are most likely to test your analytical solution, the way that if you can derive this analytical solution. So this is how you consider to get this Nussbaum number, okay, if you neglect the subcooling effect. Okay, so there is no question, let's continue. Okay, before we do that, you can also further to make this correlation a little bit more clean, okay, by introducing another dimensionless parameter. Okay, if you further define a Grashof number, and this Grashof number is defined as the density difference between rho L times rho V, right? Remember that our Grashof number before, okay, in the natural convection we are using this T of T minus T of infinity, right? Something Ts minus T infinity, T wall, T surface. In the natural convection, we're using this one. But remember, this one times beta times T actually is give you, and also times the rho of infinity, right? So, and remember that the Grashof number we use to define the use in the natural convection. This term is also the density difference because beta is a function unit of 1/k, right? And this actually there's no unit, and it's just showing that the density difference. Okay, so this will be corresponding to this term here. Corresponding to this term here. Okay, so that's why that you can also define a Grashof number for this film condensation cases with rho L times rho L minus rho V times G of L3 times mu L to the 3. Okay, you define this Grashof number for the liquid film, and you can also define another number called Jacob number. The Jacob number is defined as CPL times this exercise temperature, right? T saturation minus T surfaces, divided by H of FG, the latent heat. So basically, is the ratio of the sensible heat over the latent heat. So this is called the Jacob number. And also, you have the liquid Prandtl number, right? Which is the Cp of L times mu L divided by QL. So if you define these three things, if you think that actually the Nussbaum number, average Nussbaum number, okay, the average Nussbaum number, this one, can be rewrite as this 0.93 false rate, with this combination of this Grashof number, Prandtl number, liquid Prandtl number, and Jacob number. Okay, so this is a non-dimensional form of this correlation. Looks more clean. All right, but this is for the cases where you neglect the subcooling effect, right? And if we do not neglect the subcooling effect, okay, we want to consider this subcooling. So in that cases, okay, remember that when we neglected, right, we assume that when we neglect, we assume that Q dot X equal to this directly, right? But if we do not neglect it subcooling, so this equation need to add some additional terms to accounting for this subcooling effects. Okay, and this additional term is basically the changes of enthalpy on this control volume. Okay, so if for this control volume here, okay, you have the flow enthalpy here. You have the flow enthalpy here. Okay, you have the changes. Okay. So the heat transfer rate at the wall will be equal to this m dot dm dot times this HFG, and also minus this rate of enthalpy leaves to the controller minus rate of enthalpy enters controller. And the enthalpy is just doing integration for the liquid density times the velocity times the liquid enthalpy. Do this integration, and this will be the final result. Okay, so you will see that this additional term you have here. And this enthalpy is basically very easy to calculate, right? It's just CPL, liquid specific heat, times the local temperature divided by local liquid temperature divided by some reference point. Because enthalpy you need some reference point, right? And so in this case, we're just using the saturation temperature as a reference temperature point. Okay, so we can define this enthalpy as a CPL equal to T minus TSAT. Okay, and also because this temperature profile is linear, right? We have linear temperature profile. We assume that. So this term can be also related to this one. Okay, due to that linear correlation, so that we convert this local unknown temperature to this delta again. Okay, and also remember that this is d gamma. Okay, not dt. So this is d gamma. This is gamma. So this gamma value is you can bring this gamma value to this Q dot here. So you bring everything to this equation here, and also this Q dot dx is still same as this on the left hand side here. Okay, on this one. So you can still derive equation. I neglect some procedure in the middle. So but the result will be this one on the left will be equal to this HFG plus 3/8 CPL times T saturation minus TS times d gamma dx. Okay, this equation is what you have. And compare this equation with the first cases where we neglect the subcooling effect. Compare this one with this cases here. Now compare this equation with this equation. So what do you find? You find that these two equations, right? The only difference is this term. In the previous cases, is this term here. And in this term, like you just add an additional term here. So what does it mean? So that means that if you compare these two cases, okay, in the case one, so the only difference is that H of Fg is replaced by HFG plus 3/8 CPL times the TSAT minus TS. So this will save us a lot of time so that we do not need to do all this derivation again. Okay, what we know is that if we want to include in the effects of the subcooling, we can just replace all the solution we have here, H Nusside, local H local Nusside number, mean H mean Nusside number. We can just replace this H of G value, okay, to this value. So let's define this HFG star with this value quantity, okay, and because there is a Jacob number definition, so it can be also rewritten as this 3/8 Jacob number. You can just replace this HFG to this HFG star into this equations we derived for this case 1 when we neglect the subcooling. Replace this HFG to this HFG star. Then that will be the equations where we consider the effects of subcooling. Okay, so in these cases, okay, if you want to consider the effects of subcooling, in most cases you should, okay, just calculate this new HFG, which will be 1 plus 3/8 Jacob number, and replace this and use this one, in this original equations we derived here, so you can have the new equations for the cases where you consider the effect of subcooling. Okay. So let me get some water. Okay. So any question? So this is the most critical part of this lecture, and because that give you this Nusside this Nusside film analysis. Okay, analyzing the film condensation is the most critical part of this two-phase problems. Okay. Okay. So if you have no question, let's continue. So some discussion here. Okay. Although we derived this correlation here, right? This HFG star equal to 1 plus 3/8 Jacob number. But remember that this definition, all the equation we derived here, is based on the assumption that we assume the temperature distribution is linear, right? It's like a straight line here, right? This assumption is very, very cruel. Okay, it's a very, approximated. Okay, it's not very accurate. So there is some other people, the rational, the guy who developed that rational correlation for the bowling. He improved that this result. Okay, he didn't assume the temperature is a linear temperature anymore. Okay, he just do some numerical analysis and using some integral analysis for it. He developed a new procedure which is actually more accurate. So this assume H of FG star is equal to HFG times 1 plus 0.68 to the times this Jacob number. Okay. So in the realistic cases, okay, engineering problem, you should use this equation, not this equation here. Okay. So actually 3 divided by 8 is 0.7375, right? And this 0.68. So it's much larger than that 0.375. Okay, this is much larger than 3/3/8. So the difference is significant between this one and this value. So this is the first thing. Okay, so in the engineering problem we usually using this one. And the second case is that second discussion is that after we have this correlation, right, we want to see then that in which condition we can neglect this subcooling effect, right? And remember that this Q dot, okay, the heat transfer rate is proportional to this latent heat to the power 1/4, right? If you look at our result here, this Q dot is to this H of FG to the power 1/4 here, right? And so let's assume that we have 1% error, okay? Okay, so let's assume 1% error for the Q dot if we didn't consider this subcooling effect. So the subcooling effects can then be neglected if this 1 plus 0.68 to the Jacob times this Jacob number to the power of 104, okay, because it's the power of 104 to the Q dot is smaller than 1.01. So that means that this additional term is only contribute 1% error, okay. And if you try to derive this one, you're seeing that okay, this is corresponding to the Jacob number is smaller than 0.06. Okay, so the conclusion here is that if you really want to neglect the subcooling effect, that is only true when your Jacob number is smaller than 0.06. Okay, if your Jacob number is large, if you do not do this modification for h of g, your error, your result will be, has much error compared with the realistic result. Okay. So this is the second discussion. So in which condition that you can really neglect the subcooling effect. Okay. And the third discussion is that if the plate is not a vertical, okay, if plate has an inclination angle, okay, for this inclined plate, like the inclination angle is theta, okay, this solution is still valid if you replace the gravity g to the g cosine theta, okay. All this correlation, this HFG here, this equation here, you just need to replace this g with g cosine theta, so all the results still valid, okay. This is the third one we want to discuss. And the fourth one is the effect of superheating. Okay, so superheating is what we the region that we are talking, right? The assumption we make for this analysis is we assume the vapor is in the saturation temperature. But as I show you here, it maybe has some superheating, like the vapor is in a T infinity, not the T saturation, which will be a little bit larger than T saturation, right? And in these cases, you also need to consider the heat transfer rate due to this change of temperature from the T infinity to T saturation for the vapor. Okay, and it's also very simple to do that, because that if the effect of superheat of vapor needs to be considered, okay, the vapor, like the vapor reservoir is superheated to T infinity. Then if you're looking the enthalpy of the vapor, right, H of V, need to be condensed into the film, right, will be just equal to this HFG value plus an additional, enthalpy changes from CPV times T infinity minus T saturation. So what does it mean? This means that if you want to consider the superheat effects, okay, you just need to replace the HFG value, we have here, with this additional new HFG value with this quantity times further modify this HFG with some additional superheating component, this CPV times T infinity minus T saturation. By this way, you can, consider the superheating effects in the vapor side for this condensation, film condensation. Okay. The next discussion is that I want to let you know that the equation we derived, right? Because we think that this is a film condensation for a vertical plate, right? The laminar film condensation for a vertical plate. These are the equations we derive here. The equation we derive, here, the equation we derive here, okay, can also be working for the condensation on the outer surface of the vertical tubes. Okay, if you assume you have a tube, okay, you have a tube here, you have this vertical tube, and if you have the condensation, okay, if you have the vapor, and you will have the liquid form on this outer surface of this vertical tube, right? Not the inside, okay, outside the vertical tube. It's also working. Why? Because that the reason is very simple. Because that we usually thinking that this liquid film is very thin, okay, which means that if you compare this thin thickness with this arc length, okay, of this the changes of this arc direction, this arc length. It's very small. Okay, you can thinking that it's still like a flat plate because this film is too thin. Okay. Okay. So that means that all the equations that you derived before is usually you can still thinking that working for you have vertical plates, vertical tube, film condensation on laminar film condensation outside, okay, outside of vertical tubes, vertical tube, okay? Not tube. So this is another thing I want to let you know. And the last thing is that although, okay, as you see that to obtain this analytical solution, right, we make so many assumptions here, but it turned out, okay, the correlation we obtained through this analytical solution, okay, comparing with the empirical data, it's the result. It shows that the result your analytical solution is pretty good compared with your numerical data, which means that although we make so many assumptions, but this correlation is still showing very fairly accurate results. Okay, pretty accurate, fairly accurate results. Okay, so this is this new cells analysis for film condensation. So this is only working for laminar flow. Okay. Another two flow regime is VV flow regime and the turbulent flow regime, right? And in these cases, okay, we won't have the analytical solution, so we go back to the empirical correlations. Okay, and first go back to look what we defined the Reynolds number, right? As we told you, Reynolds number is defined as 4 delta times rho of L times U of mean divided by mu L, right? Because this 4 delta is the hydraulic diameter we were showing before, right? And what's this mean velocity? So this mean velocity calculated based on the local mass flow rate, this gamma, divided by liquid density times this cross-sectional area length, right? Delta, right? Because that you have this right at this location, right? You have gamma, so you need time density and time divided by this length delta. You get the mean velocity. So if you bring this equation mean velocity to this Reynolds number, you can rewrite your Reynolds number to be 4 gamma divided by mu of L. Okay, so which means that your Reynolds number can be calculated directly from your local mass flow rate. Okay, and also before we're showing that based on this Reynolds number, local Reynolds number, you can seeing that the flow either in the laminar, VV, or turbulence based on this, right? And for the laminar cases, right, we have this result here. We have this Nussbaum number, mean Nussbaum number result for laminar cases, right? Or you can see that this is our result. And remember, this Nussbaum number is based on if you're using length scale of big L, right? Which is the plate length. Some researcher, okay, some people like to using another length scale to define Nussbaum number, not using the L anymore, okay? The plate length. They're using this one. This is mu is kinetic nu, okay? Kinetic viscosity of the liquid divided by the gravity acceleration constant and to the cube. So this will bring you a length scale, okay? In the unit of meter. So they're using this length scale to define a new Nussbaum number, okay? And by doing this, and also from this result here, and also assume that your rho of V is much smaller than rho of L, so you can remove the rho of V by some assumption, and you can write another form of laminar flow where the Nussbaum number will be just equal to 1.46 times the Reynolds number to the -1/3. Okay, just rewrite that equation to make it. So to do that, you know, as I said, I told you that we're using a new length scale, and also we do some small assumption like to neglect the, you know, the assume that rho of V is much smaller than rho of L. And in this case, this is Reynolds number, right? Because it's the mean, right? Mean value. So this Reynolds number will be equal to 4 gamma divided by mu of L. And this gamma is the total. If you consider mean, if your mean is mean along this plane length, right? So this gamma is the gamma value at here, okay, at this location. It's the total condensation rate of the entire plate, okay? So this is Reynolds number means, okay? And similarly, we have the empirical correlations for VV regime and turbulent regime, right? We have, you can find many this kind of empirical correlation, right? Even from the new published paper these days. So this is some example, okay? And this Nussbaum number is also using this new length scale to define. So this is some correlation like in the VV regime when the Reynolds number between 30 to 1800, it can be to this value for the VV flow. And for the turbulence, you can use this one. All right. So this is the heat transfer rate. This is the heat transfer rate for the VV and turbulent flows. You know, some empirical correlations available. All right. Okay. Let's also talking about a little bit more. Okay. So previously, you know, we're focusing on the film condensation on the vertical plate. So there are also some other geometry where you can also apply the same Nussbaum's analysis to derive the analytical solution for laminar flow. Okay, so you know, if you get interested, you can, you know, read more about this. But for example, like you know, condensation on horizontal tubes. You have a tubes here horizontally, and you form the you know, fumes, you know, liquid film on this surface outside of this horizontal tube, and it's going down at the bottom. You can apply the same analytical method of the Nussbaum analysis on this problem, and this will be the result. Okay, and Nussbaum number with the Nussbaum number on the diameter of the tube, and will be this value. Okay, and another one is that if you have multiple tubes, which you form two banks of these horizontal tubes, so your condensation from the top, and then drop into the second tube, and drop into the third and the fourth, and continue. So this Nussbaum number you will have an additional correlations. Okay, so you can derive from this one basically using some you know, serious analysis. Okay, because that the inlet condition with this one will be the outlet condition with this one, right? So you're just doing some serial analysis. You're showing that actually for the, if you have n tubes, okay, if you divided by one tube, their ratio will be 1 over n, 1 over minus 4. This n is the number of tubes. Okay. Another thing is you need to know is that so this is the, you know, the film condensation on the horizontal tubes, right? And also we're talking about that. You remember we're showing that on this discussion is that for the film condensation on the vertical tubes, we can still using the same correlation for the vertical plates correlation, right? So we have the both condensation on vertical tube and condensation on the horizontal tube. There will be, so this, if you compare this result with this result here with this result here, because this is for the laminar cases, right? For the horizontal, for vertical plate, which is also working for the vertical tube. It will showing that basically you can write that this h of vertical tube, okay, vertical tube divided by this h of horizontal tube Okay, this one divided by vertical beam, it will be equal to 1.29 d divided by L. D is the diameter of the tube, and L is the length of the tube, to the power of 1/4. Okay, so this means that it depends on your diameter to the tube length ratio. Okay, you will know that whether or not this vertical condensation will be better than horizontal, or horizontal will be better than vertical. Okay, not certain. Okay, it depends on this whether or not this value is larger than 1, right? So it depends on this ratio between D and L. So there will be a special cases that these two will be equal to 1. Okay, the heat transfer coefficient on the vertical direction and on the horizontal direction is the same. Okay, so you can calculate that one yourself. Okay, so there's some correlations related here. Okay, so we finished the film condensation, and so the last topic, okay, which we will finish today's lecture, is the dropwise condensation, right? So we at the original we're seeing that the condensation, there are two types, right? The film condensation and dropwise condensation. So for the dropwise condensation, we already knowing that the dropwise condensation is usually predict, much higher heat transfer rate than the film condensation. So the question is that, is this the ideal case we want to achieve? Because that, as you know, since this is larger, right? So that means that if we want to do heat transfer, right, maybe we prefer the dropwise condensation rather than the film condensation. Theoretically that it is true. If you can maintain the dropwise condensation, that is true. That is really the better one. But there is some challenge here. Okay, usually it's not very hard. To form to create a dropwise condensation. Okay, so the challenge is not to achieve it. Okay, but the problem is that after you have the dropwise condensation, usually it's very hard to maintain it, to sustain it. Okay, to sustain it is very difficult, because that when the condensation going on, you will have more and more liquid on the plate, right? Your droplet will become larger and larger. So eventually, they will become to the film condensation. Okay, so practically, okay, it's very hard to sustain it. Okay, this is the one thing you need to know. Although it's good, but it's hard to achieve, to sustain, to maintain. Okay, and also the dropwise condensation, because we know that this will be a more complicated problem, right, compared with the film condensation, and because this random location with these droplets and this kind of thing, we won't have the analytical analysis on it. So the people these days, the people doing is that still study it empirically, and we will have many in literature. Okay, you can find many empirical correlations based on the different fluid and surface combination. Okay, what fluid will be and what the surface will be. Okay. Some example, this is the one example that the steam on the copper surface, they think that the droplet heat transfer coefficient, dropwise condensation heat transfer coefficient will be just this value. The function constant if it's superheating, and if it's in the equilibrium state, it's just a function of the linear function of saturation temperature, something like this. Okay, so this is basically we're concluding that what we can do for the dropwise condensation, and that's it. Okay, this is the basically what we have today. So for boiling and condensation, and again, okay, this is not required for the exam. Okay, so because that I don't think we have time to have another homework to practice it. Okay, so we will not have this in the exam. And but it's useful. Okay, it's useful for your qualified exam. It's useful for your research, and it's useful for your future work if you go to industry. And that's it. So we will finish our today's lecture here. This will be the last one, and the only left is the final exam. And tomorrow I will write you guys an instruction for the final exam. So the final exam again is on May 18, okay, Monday. Okay, it's a Monday, and starting at 5:30 p.m. and 24 hours of our open book. Contents is cover all the book contents, okay? Not book content, all the lecture contents, except this one, okay? Not for this one. And the contents after the midterm exam will be account for 60%. So that means that there will be still be 40% final exam problems for the contents before the midterm exam. Okay. Any more questions, guys?
Will you be holding an office hours between now and the test?
Yeah, next Tuesday I will still hold the office hour. Okay, so definitely next Tuesday will be here. And if you need an individual one, need more time, you can write me an email to schedule. So if you want, but I prefer the next Tuesday, so I can still hold the office hour at the same time, from 2 to 3. Okay.
Thank you.
Yeah. I will try to grade your homework, the latest homework, and post the homework solution in a few days. Okay, so that you can use it to prepare your exam. Any more questions?
Do you curve the class?
Yeah,
Very
it's
cool.
showing the I write it in the syllabus, right? I do curve the exam. So basically, the way I'm showing it, what I'm doing is that after I calculated your overall grades, right, for everyone. So the highest grade in this class will be curved to the 100 points, right? And also I will, choose some grade on the bottom one to make sure that the major part of the if I believe you doing good, okay, you do all the homework, you do okay with the exam, you will be passed. No worry about that. Unless you're doing very, very bad for the midterm, for the final. But at this point right now, from the midterm, I do not see anyone can fail. Okay, that's the thing. So
All right, sounds good.
yeah. So but you need to prepare well on the final. Okay, and pay the time on it, and you should be okay. Okay.
All right, thanks.
No problem. Any more questions? Okay, so then if there's no question, I will, I will just stop and finish this lecture. I will same thing. Okay, I will post this lecture notes and the video on the Blackboard. So you do not, although this is not inside the exam, so but you can still keep it, and if you want to use it later. Okay. All right. So in the end, thank you for everyone to cooperate for this semester lecture. So this is the my first time, the first time for me to teach a graduate class, so for the whole class. Okay. And also that because this pandemic break, I know it's difficult for you, for me, but thank you for everyone to overcome the difficulties to attend the lectures, to finish the homework on time. It's not easy, but I'm sure everyone, from what my point, okay, I see everyone really do a good job, because I didn't see anyone for late submission of the homework I didn't see anyone, okay, not a single person that to miss an exam or something, sorry, miss the homework. So thank you very much, guys. Okay, doing your best for the exam, and let me know if you have more questions. Okay, bye everyone.
Thank you.
Okay. Thank you.
Sure.
Thanks.
Yeah, stay safe, everyone.
You too.
Yeah, do not do not thinking that this virus is going away. Okay, it's still dangerous.
Take care.
Okay. Take care.
Take care.
Bye.